Hello, everyone. Namaste and Jarle. Today we are going to review about wave. How can we write down the wavelength for a given length of the string? So we are specifically dealing our wave case in case of string or thread. So the wave is confined in the string or thread. In that case, how can we calculate the wavelength and the antinode, and what is the node? What is the relationship between antinode or node with the case of wavelength of the wave, and then the length of the string provided over there. So this is our topic related to that case. I think this will help you a lot. Let's consider a traveling wave or uh, moving wave. We can say it as a progressive. If this is the source of the waves that is producing the wave, this wave will be propagated like this. For simplicity, we are taking a transverse wave, not a longitudinal wave. So, and if this is the mean position or equilibrium position, right? So how do you define transverse wave? Transverse wave, this is the direction of propagation of the wave. So this is the wave is propagated from the source to the destination. This is the destination point or observer. You can say it as observer as well. So when the wave is produced from source, it propagates towards observer. This is the direction. And if the vibration of the particles in the medium is perpendicular to the direction of the wave, in this case, these are the vibration of the particles present in this medium between source and destination or observer. So the vibration of the particles is perpendicular to the direction of propagation of wave. So such type of wave is known as transverse wave. So this is a transverse wave. There is a longitudinal wave as well. So in the longitudinal wave, it is not in the vibration of the particles is not in the direction of the propagation. Instead of that, it will have in the direction of the propagation. So the vibration of the particles will be like this. So it will be vibrating to and fro in the direction of the propagation of the wave. So this is the direction in which the wave is propagating, and this is the vibration of the particles. So we can take example of sound wave in a gas. In a gas. So sound wave in a gas or sound wave traveling in a gas medium is a better and best example of longitudinal wave. So I am speaking a wave that I produce is a sound wave, and that sound wave is propagating in a gas medium. So it is a longitudinal wave. But sound wave can be a transverse wave as well. That is the case of the wave propagating in the stream or thread. So that is our topic we are going to deal with. So let's forget about longitudinal wave for now, because we are dealing with the wave in the string. That's why the wave in the string is transverse wave. It also depends on the method by which you are producing the wave in the string. So if you plug a string, example of the string in the guitar. So now if you plug it somewhere in between the two fixed points like this, then it will vibrate like this. Or yeah, so this is a transverse. You got the idea of transverse and longitudinal transmitting from source to the destination. So it carries a certain amount of energy while traveling from source to observer, and it is in motion. That's why it is a transverse wave or moving wave or progressive wave, because with every stand of time the wave is transmitting or progressing from source to the destination. That's why it is a transverse wave. Let me take the snapshot of this traveling wave. I'm taking the snapshot of this person only. The snapshot of that person is this one, right? Now, let me define this term. So, this is the mean position. I already told you this is the mean position or equilibrium position. Vibration of the particles is above the mean position as well as the below the mean position. So, the maximum amplitude that takes place above the equilibrium or above the mean position is known as the crest. So, this one is the crest according to the definition crest. And the maximum displacement that is taking place below the mean position is known as the trough. So this one is the trough part of the wave, right? So this is the crest, this is the trough, and the maximum displacement of a wave above or below the mean position is known as amplitude. So this is the mean position, and maximum displacement is over here. Maximum displacement taking place in the wave. So these are the amplitudes. Maximum displacement in either direction above the equilibrium position or below the equilibrium position is known as amplitude, and if it is taking place above the equilibrium, that part is known as crest. The maximum displaced position is crest, and below the equilibrium position is known as the trough. That is the point. Trough is the point, right? So now let's define wavelength. The wavelength is defined as the wave consisting of one crest and one trough position. So the wave consisting of crest and one trough gives you the wavelength of that wave. So it be represented by lambda, right? And there is also another characteristics of the wave, that is the frequency of the wave. Frequency is number of cycles, complete cycles, number of complete cycles or complete wave over unit time. So the number of complete sites completed, number of complete waves completed in unit time is known as the frequency of that wave. So in this case, if this is a wave, as I already told you, one crest and one trough gives you the wave, and the distance between the wave and the distance of the wave is known as the wavelength, right? One trough, one crest, one trough, and the frequency is the number of complete waves divided by unit time. That is the frequency. So we know the frequency, we know the wavelength, and we know the amplitude, we know the crest, we know the trough. Now let's go into the speed of the wave. As I already know, distance over time, right? Or displacement over time. So distance in this case is wavelength, that is lambda, and time, that is t. Now, if we are taking in a complete cycle, then this 1 by time is known as, because in a complete cycle, this time will be time period, right? So lambda over time period is known as the frequency. 1 over time is the frequency according to the definition of frequency and the time period. So this is the mathematical definition of the speed in case of wave. So speed v is equal to the distance, that is wavelength, times frequency. This is the character. These are the characteristics related to a wave. Because we are just dealing with a simple case. That's why we have to know these things: speed, crest, trough, frequency, wavelength. These are the simple things we have to know in order to understand the wave. Now let's move into the second type of wave, that is standing or stationary wave. So in this case, the wave is not moving at all. Rather, it seems to be it is standing in a confined position. So for example, because we are dealing with the standing wave, in case this is the string which is tied at its both ends. So these are the both ends tied to each tied at the distance, at the separated distance. So if standing wave is created over here, then it would be like this. So wave going from one position, hits at other position and gets reflected back to the initial position. So this is the nature of the standing wave. like this. Now, if you see this wave is not moving at all because this is confined within this region, within these two region, or within these two fixed points in the string. So this is the string, length of the string, right? So this is the length of the string, length of the string, right? Let it be represented by L. So within this length L, the wave is confined between two fixed points. These are the fixed point, fixed ends. So end, it is fixed. This is also end, that is fixed end. So now this wave does not carry energy because it is not propagating, it is confining within the region, right? So the simple description that it does not carry energy, it is confined within the region. So if this is the source that we looked in our video, so this is the source producing the wave, and when it hits when it strikes or hits on the string present over the pulley, because in our video there was like this was like this. So this, there is the pulley, this is the pulley position, and this is the vibrator position. So this is the vibrator, and it is hung with a certain mass or load, right? So two things are the fixed points that you describe here, this one and this one, right? So this is the vibrator, the source producing the wave, and this is the fixed point. The wave can be like this, or the wave can be like this also, as we have shown in different case, like this also, right? So depending on the condition, it can have different segments of the wave. So in the first case, we have this one, only one segment. Wave going in this direction and returning back this direction. Due to superposition, the resultant wave will have zero displacement, zero amplitude, and that will giving us no energy at all. And in the second case, depending on the condition, we will be having two segments. So first segment and second segment. First segment, second segment. The wave going in this direction and returning after striking on the fixed end at other end, it gets reflected back to the initial position. So again, the resultant wave is has zero displacement, so it doesn't carry energy, right? So this is two segmented wave. And in case of three segmented wave, in case of three segmented wave, so first segment, second, oh, it becomes fourth segment. There. One, two, three, fourth segment. Let's go into the three segment wave. One, two, and three, right? Three segmented wave. So depending on the conditions, we can have different segments of the wave in a fixed length of a string. So let's go to the definition of the segment or stANDing wave. The maximum displacement in either direction for the traveling and reflecting reflected wave is known as the antinode. This is the position of antinode, A, N, or you can simply write A only, antinode. And the minimum position or the minimum displaced position of the particles, that is going to be here, right? So this is denoted to be node. So these are the new terminologies we have to understand in stANDing or stationary wave. This is antinode, this is antinode, these are the nodes, 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 antinode, antinode. Antinode, 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 node, 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 antinode, antinode, antinode. These are the nodes, 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 right? So let's go into the distance between the antinode and another antinode, and distance between node, and what is its relationship with the node and antinode. Let's go into the main part of this video, right? Now, In previous video, the case of traveling wave, I have drawn like this wave, right? So this is the starting point. The wave starts, and I'm just taking only 2%, that is crest and the trough. So this is going to be the wavelength according to our definition in the first part, beginning part, right? I have taken three segments of the three different cases of standing wave. This is the first case, this is the first case, and this is the second case, and this one is the third case. So I have first segment or first loop, second loop, third loop or third segment of stationary or standing wave of a fixed length of the string having length L, right? So now if I look at the first segment of the or first case of the standing wave, this is the starting point, this one is the starting point, and this one is the ending point. So it is taking a part of the wave, right? So if I compare the segment of the wave with this segment, with this case of the wave, then the first segment of the wave or first case of the standing wave is taking place only this part, or it is taking wave of this part only. So as we already defined the wavelength, so crest and trough gives you the wavelength lambda, right? And this is the half of the wave. So in this case, this is lambda over 2. So the wavelength associated with this wave, standing wave, is the wavelength divided by 2, or the portion of the wave constrained in these two fixed ends of a string of length L, even though the length of the wire is not looking to be same, but they have got the same length of the same length. Uh, right, do not get confused. So in this case, first case, standing wave is taking place or taking a half of the wavelength. uh, this is the half of the wavelength, right? You got it, right? I think so. And this is also the distance between two consecutive nodes. So this is node and this is node, right? So distance between two consecutive nodes is given by lambda over 2. This is the mathematical definition between the two nodes present in the standing wave. Now, if I look at the distance between the node and the antinode over here, then this is the segment of the part. This is the segment of the wave, right? In the standing wave. So this is the part I'm going to look at. So node and antinode. Now, if I compare this figure with this one, this is the starting point, and it has gone to the maximum dispatch position. So I'm only taking this part only, right? So how much is the distance between the node and the antinode? So if I look at the distance in terms of wavelength, then I know this is lambda by 2, right? Then this is again half of the lambda by 2. This is lambda by 2, lambda over 2, and this part, it is half of lambda by 2. So the overall value will be lambda over 4. So what does it mean? It says, or it means, the distance between node and consecutive antinode is lambda over 4, while the distance between two nodes, consecutive nodes, is lambda over 2. If I take the distance between two consecutive antinodes, then this is again going to be lambda over 2, because this is the antinode and this is the consecutive antinode in the other part, in other segment of the segment of this of the same stationary or standing wave. So this is lambda over this part is lambda over 4, and this part is lambda over 4. When I sum of it together, then it will be giving me lambda over 2. So the conclusion is that in a standing wave, the distance between two consecutive nodes is lambda over 2. The distance between two consecutive antinodes is lambda over 2, while the distance between node and antinode is lambda over 4, right? Because we have to deal this case in many situations. So let's go into the conclusion part, right? So what does it say is that distance between the first case, the distance between node and consecutive antinode is lambda over 4. Second conclusion, the distance between node and another consecutive node is lambda over 2. And third conclusion is the distance between antinode and another consecutive antinode is again lambda over 2, right? So these are the conclusions I get from the stANDing or stationary wave. Now let's compare this node and antinode with case of the length of the wire or length of the string present over here. So if, as I have assumed that the length of the wire is L, so this is L, this is going to be L. So L is equal to lambda over 2. So in case of wavelength in case of length of the wire is 2 times of L. And this is the first segment. This is in the first segment or first case of the stANDing wave. So in the first segment of the stationary wave, the wavelength of the wave is going to be twice of the length of the string used in our case of the formation of stANDing wave or stationary wave. And in the case of second case, now we can get the clear definition, right? So antinode, this is antinode lambda by 2. The number of antinodes taking place is 2 times, right? So it is lambda. Or this is lambda by 2 because we know the distance between two nodes is lambda by 2. And this is again another nodes, consecutive nodes. So this is lambda over 2 and this is lambda over 2. So when I add up these two lambda over 2, I'll be getting lambda. And this is going to be equal to the length of the wire, right? I think you got me, right? Now we can define wavelength in terms of antinode as well, the number of antinodes as well. So in this case, there are two antinodes. As I already told you, the distance between two consecutive antinodes is lambda over 2, right? How many antinodes are involved in this case? So the number of antinodes involved in this case, 2. So 2 times number of antinodes, that is number of antinodes is 2 and antinodes is an, so it is going to be equal to 2. As I already told you, the distance between two antinodes is lambda by 2. If there is involvement of antinode, then it is lambda by 2, right? So when I simplify it, it is giving to be lambda. In this case also, the number of antinodes involved in this case, in this first segment or first case is 1. Number of antinodes involved in this case is 1 and antinode. So it is again going to be equal to 1. Antinode is lambda by 2. That is lambda by 2. In this case, antinode 1, first, second, third, right? So if I want to compare antinode with case of the wavelength, number of antinodes involved is 3 antinodes. 3 antinodes are there. So 3 antinodes is lambda by 2. So the overall wavelength in the third case, that is third segment or third loop in the third loop of the stationary wave is 3 lambda over 2, right? And this is going to be equal to the length of the wire present in that section. That is, according to assumption, that is L. So if we want to deal with node, this is the initial position, right? Or even though it is a node, but it is the initial position, right? This is the first node, this is the second node, and this one is the third node. So again, 3 times node is going to be equal to 3, and as we already know, the distance between two nodes is lambda by 2. So again, is 3 lambda by 2, right? In either case, if you deal with antinode or node, the wavelength is going to be the same, right? It does not change. It must not change because this is the wave, right? And it must not change with the involvement of the antinode or node. So this is the simple thing you have to consider in order to write the wavelength in terms of antinode and node, and its relationship with the length of the wire or length of the string present in that confined section, right? So in general, the conclusion is first part. The distance between two consecutive nodes is lambda over 2. Second, the distance between consecutive antinodes, that is antinode and antinode, is lambda over 2. Third, the distance between node and consecutive antinode is lambda over 4. And fourth, its relationship, the number of nodes and antinodes is related with the length of the wire or length of the string present in the confined section is number of antinodes times antinode or node, that is going to be equal to number times lambda over 2, that is going to be equal to the whole length of the string, right? So these are the conclusions that we can get from this part. I think this is a short video that will help you in analyzing the nodes and antinodes, its relationship with the wavelength and its relationship with the string. Thank you. Bye bye.